let's explore generator methods. And we'll use the Fibonacci numbers, an infinite series of numbers, to do this. Here we have this Fibonacci numbers that are defined to be 1 and 1, and apparently I left one out. And then the next one is the sum of the previous two. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and so on. Now this is an infinite series of numbers. So let's write a function, a traditional function, like you've seen us write with lists and building up the data and then passing it back to generate this. All right, so we're going to define a Fibonacci function. Initially, I'm going to give it a limit. If there's no limit, you'll see we'll just flat out run out of memory and crash our application. So we're going to have something like a list that holds the numbers. And then we'll have, the way you compute this is you have a current number and you have a next number. Then I'll say while current is less than a limit. And the implementation in Python is actually really fantastic. So what you do is you can use tuple projection and avoid having a temporary variable. A lot of times you'll sort of see 3 steps to do this. We can do it in like 1. It's cool. So we'll say current, comma next. We'll do that's the variables, and we want to do a tuple unpacking into them. So current is going to be signed next, and next is going to be next plus current. And then we want to add to our numbers current. And then we're just going to return the numbers. So let's print the Fibonacci, and let's say we want all the Fibonacci numbers that are less than 100. And we still have the factorial stuff above, but don't worry about it. Just pay attention to the last line. So here are our Fibonacci numbers, computed up to and sort of including the last number there. So let's actually print this out in a slightly different way where we have a little more control to go through. So let's say for n in Fibonacci, like so. Then we'll just print n, and we'll do that end equals just a little comma thing. So we can have it on the same line. Let's run that. Perfect. It looks basically the same. But here's the key thing. Let's put a breakpoint here and actually step through. We'll actually step through this function call. Now, there's nothing fancy here. There's nothing that should be surprising to you here. We're just going to step into this code and step through it. So we're going to come down here. I want to say, while this is not the case, we're just going to step along. You can see on the right, the numbers are changing. 3, that should be 5, and then next should be 8, and so on. And we're building up this list of numbers. Here you can see the list. Oops, I can't highlight it. But here you can see this list is building up. It's got the 8. And all of the computation is happening in this method. And then, in the very end, when we decide we've had enough, a few more will be there, then we return it, and then we loop over it like so. Okay, that's how traditional methods work. But what I'm about to show you is not a traditional method. It's something called a coroutine, and it's extremely powerful. So let's take this same method and let's define a second variation of it. So let's call this Fibonacci Co. And down here we'll call Fibonacci Co. Now we're going to take 2 steps to go through this and understand it. First, we're going to just change this to work exactly the same. And then we can see we could even do better. So instead of letting all the work happen in the Fibonacci method and then processing the results, what would be better when we have these large sort of pipelines of data processing would be to pull one back and inspect it, do a little work with it, then throw it away. And then pull the next one, inspect it, do some work with it, throw it away. And that way, even if we're processing a billion items, we only pull one into memory to work with at a time. And you can see that we'll do the same thing here. So instead of putting this into a list, we can use this keyword called yield. So I can come over and I can just simply say yield current. And the way this works is when I start using the yield keyword, this becomes a coroutine. And when I say yield some item, I'm basically declaring to the Python interpreter, what I want you to do is create a sequence that can be one item at a time computed. And here's one of the items. Every time I say yield something, I say, here is one of the items. I never have to return all the items at the end. I just say, here's an item, here's an item. And when I stop saying, here's more items, then that's the end of the sequence. Let me just do some quick formatting here so that things appear correctly. So we'll say via list and via yield. Now let's run it. I can see via list, we get those numbers, and via yield, look at that, we get exactly the same thing. But have we really gained anything? I mean, okay, we have this cool yield keyword and we don't have to have the list. That got a little shorter, but what you'll see is we've actually gained something tremendous. So let me put a breakpoint here and debug it again. So we'll step in. Now this should look kind of similar. We'll step along here and we're computing the first round. And before we were adding it to our list, but watch what happens now if I step into this. Well, I'm back here. I only computed a single item, right? Notice that N is a 1. And now if I go around again and I step in again, watch, we should go straight to line 49 or maybe 47. Yeah, straight back to 47. We're not rerunning this method. We're resuming this method right here. And if I step, then we step down here. Now N is 1 again because that happens twice. And if I step in again, here we are, N is 3, and so on. So as we get them back, we get the first item, and we've only had to do enough work to compute the first item. Moreover, we don't have to put this into a list to gather up all the results and then return them. You know, we're never holding on to all the results at once. We're just giving an item at a time. So to make that point kind of extreme, let's suppose we wanted all the Fibonacci numbers, the infinite sequence of numbers. We could remove this limit and we could just say, I want to do this forever. Now, obviously doing this forever is going to sort of be a problem. It won't crash. It'll just keep going and getting slower and slower and so on. But it does let us down here as a consumer decide when we've had enough. So we could say if N is greater than 1,000, then break. But we have access to the entire infinite series. Now, if I did this with the list, this would just run for a long time, run out of memory, and then crash. But that's not what happens here. We just get one, compute the next, and any step along that path is super cheap. Basically a couple of additions and a return value. So let's run this again. Boom, look at that. With yield, we got the infinite series of numbers, and it only took microseconds to compute it. All right, and you can take these generator methods and combine them with other generator methods and create a pipeline of processing. And that's exactly what we're going to go do in our file searcher app.